The last two big ticket items are billing and social login. I won't implement them with adherence to the way were implemented by Uber. I want to keep both of these features simple, as they are both very volatile features and requirements within both of these APIs can change literally overnight. I will implement billing as a request before the ride starts. I'll use Braintree to do this mostly because it's already implemented in Codename 1. The original implementation in Uber checks whether a billing method already exists. This is possible to do in Braintree, but it would require some extra work. To keep billing simple, I'll just charge $1 per minute and do the charge in the server side. In-app purchase is one of the big ticket features in mobile apps. We support this rather well in Codename 1, but we can't use in-app purchase for this case. In-app purchase was devised as a tool to buy virtual goods inside an application. This reduces friction as no credit card is needed. Google/Apple already have it, and makes purchases more fluid. The definition of virtual goods has some gray areas, but generally the idea is that a good or service sold would be something that has no immediate physical cost. Good examples of virtual goods would be in-game item, upgrade of software functionality, app subscription, etc. However, physical items and services are explicitly prohibited from using in-app purchase. This isn't a bad thing. In-app purchase takes a hefty commission of 30%, which isn't viable for most physical goods sold. Braintree is a part of PayPal and provides an easy-to-integrate mobile payment SDK for selling physical goods and services. In theory, we could just collect a credit card and call it a day, but that's naive. Securing online transactions is a nuanced task. By using a trusted third party, a great deal of the risk and liability is transferred to them. One of the core concepts when working with the Braintree is opacity. The developer doesn't get access to the credit card or billing information. Instead, a nonce and token are passed between the client and the server. Even if a security flaw exists in the app, a hacker wouldn't gain access to any valuable information as the values expire. This diagram covers the process of purchasing via Braintree. Let's dig into the pieces within it. The client code, our mobile app, asks our server for a token. The server generates a token with the Braintree server code and returns it. A client token is a signed data blob that includes configuration and authorization information needed by Braintree to associate the transaction correctly. It can't be reused and should be hard to spoof in an attack. The mobile app invokes the Braintree UI with the token. That UI lets the user pick a credit card or other payment option, for instance, PayPal, Android Pay, Apple Pay, etc., then communicates with Braintree's server. The result of all this is a nonce, which is a unique key that allows you to charge this payment method. Our app now sends our nonce to our Spring Boot server. The server uses the server-side Braintree API and the nonce to charge an amount to the payment method. Notice that the amount charged is completely up to the server and isn't part of the client-side UI. The Braintree SDK for Java is pretty easy to use. We already have it in Maven, but just in case you skipped those lines, this needs to be in the POM file. Next, we add a Braintree service class, which is remarkably simple. These values should be updated from Braintree and Sandbox should be updated to production once everything is working. This is the client token that we use to identify the transaction. Notice we generate a new one for every request. We save the nonce into the ride object. This assumes payment authorization happens before the ride is completed. Once the ride is finished, the nonce is instantly available to perform the charge. Before we proceed further, the obvious next step is the web service to match. It's mostly trivial, but I'd like to point out a small nuance. Pay isn't mapped. We invoke pay in the server, so we don't need to expose it to the client side. That code requires some unexpected changes, which I will get to shortly. The first change was pretty predictable though. We just had to add a nonce field to the ride class. Here's the part I didn't expect. I needed to add the ride ID to the user object. A driver has a reference to the ride object, which is why we didn't need this up until now. However, when the user tries to pay, he can't set this anywhere else. Unfortunately, there is no other place where the nonce would fit. Since it's transient, we can't add it to the user as we'd want some logging. The ride object is the right place for the nonce. To get this to work, I had to make a few changes to the acceptRide method. I added the ride reference to both the driver and passenger for future reference. I moved these lines downward because the ride ID will only be available after the ride's save call. Since payment is handled on the server side, we can go directly to it even before we do the client side. I've decided to do this in the finish ride method. A ride that was finished before it was started is effectively cancelled. A ride without a nonce can't be charged at all. I used the route, which is ordered based on time, to find the start time of the ride. I then go to the last element and find the end time of the ride. Assuming the ride has more than one waypoint, otherwise end time would be -1. We can just charge $1 per 60 seconds, and payment is effectively done on the server. Again, I oversimplified a lot and ignored basic complexities like the driver forgetting to press finish.